All right. So I will, after that introduction, briefly mention that the reason I was a physics major in college is because I thought no one ever made a living as an astronomer, so I thought I had to do something more practical than that. But I gradually found my way back into astronomy and eventually got a job doing it. So today I get to tell you all about extrasolar planets. So before I start, I just want to point out, you guys may have noticed all these little crosshairs kind of moving across the projector. Each one of those marks the position of a star with a planet orbiting it. So there are more than 10,000 planets and planet candidates, things we think are probably planets, that we've now discovered orbiting stars near the sun. So this is just in our local part of our local galaxy, not even very far away. But that's a really big change from 10 or 20 years ago. So back when I was going to college, I tell my students I could count all of the planets on 2 hands. So that's been a big change and it's been a lot of fun. And so what I wanted to do today is to give you guys a little bit of a guided tour through that sort of zoo of planets that we've been discovering, to talk about what are some of the different kinds of planets that we're finding. And if we want to do more than just make a list with names, we want to know what kinds of planets they are. We want to know if they have atmospheres. We want to know what the atmospheres are made of. So I'm going to tell you a little bit about how we kind of study those planets in detail. All right, so if we want to find and study planets, we can make a to-do list for the things that we need to do. The very first thing on our to-do list is we got to go and find some planets around nearby stars. And maybe we can make that even into a little bit of a demographic study. So we want to not just make a big list of planets, we want to actually turn that into some estimate of how common different kinds of planets are around stars. So if I pick a star at random in the sky, can I tell you what are the odds that that star will have a Jupiter or an Earth or, name your planet? Once we have our list of planets and some idea of how common or rare they are, we want to know what kind of planet is it. So often when we first find a new planet, we might know the size. Is it big like Jupiter or small like the Earth? But that doesn't necessarily tell us what the planet is made of. So we might want to know, is our newly discovered planet mostly rock and metal like the Earth? Or is it mostly hydrogen and helium gas like Jupiter or Saturn? If it's a rocky planet like the Earth, even though Earth is mostly rock and metal, Earth has this thin layer of atmosphere on top of that rock, and that atmosphere is really important to us. We would not be here breathing if it wasn't for that atmosphere. So especially when we think about looking for other planets like the Earth that might be habitable, we really want to know what their atmospheres are made of and how thick they are. And so that's our to-do list. So I'm going to walk you through point by point, and we'll go through some of the things on our to-do list. Okay, so very first thing, we have to go out and find those planets. And we have a problem, which is that stars are really, really bright, and planets are very, very faint. And if I'm looking at one of those stars in the sky, that planet's really faint, and it's really, really close to the star. So it gets hidden in the glare of the light from the star. So if we want to find that little dim planet, we have to be a little bit sneaky or clever. One way that we can do that is we can look for planets that actually pass in front of the star as seen from the Earth. So I'm going to show you a video on the left. Do you see that little black dot going across the star? So that little black dot is Venus going in front of the sun. So when Venus goes in front of the sun, Venus blocks part of the light from the sun, and if we were an alien observer measuring the brightness of the sun when that event happened, we would be looking and we would see that the sun would get a tiny, tiny bit dimmer for a couple hours, and then it would get brighter again. So we could make a plot showing the brightness of the star over time, and we see it's constant, 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 little dimming, comes back up, back to being constant. So when we do these surveys, one of the best ways that we have to find planets is to look at a whole bunch of stars, to measure their brightness, and to look for stars that get a little bit dimmer on some sort of regular schedule. So once every day, once every year, once every 5 years, that star gets a little bit dimmer, and that tells us there's something in orbit around it that periodically blocks part of its light, and that helps us make a list of planets. Okay, so there's one other catch. which is in order to find planets this way, we need the planet to go in front of the star as seen from Earth. If the planet's really close to the star, the orbit can be tilted up, tilted down, and we still see the planet go in front of the star. When the planet's really, really far from the star, you move that orbit a little up or a little down, and now the planet doesn't go in front of the star anymore. So the probability of seeing that transit when the planet goes in front of the star is way, way higher for close-in planets and much, much lower for distant planets. So of those 10,000 planets and planet candidates that I mentioned that we've found so far, the vast majority of them are very, very close to their star, like closer than Mercury is to the sun. So most of what we know about other planetary systems is very strongly slanted towards the inner parts of those systems. Okay, so what do we know from these surveys? We know that it turns out that the solar system is not particularly representative of all the types of planets that we see out there. So just to get things in context, this is the inner part of the solar system. Distances are to scale, planet sizes relative to each other to scale, but I've exaggerated the size of the planets, otherwise there would just be little points on this. So relative planet size, relative distance. All right, so now let's throw up a couple of the planetary systems that we found in these surveys. Here's one. So this is a system called Kepler-11. It was discovered by the Kepler telescope. And you'll notice that there are 5 planets inside the orbit of Mercury and a 6th one just outside. And all of those planets are a fair bit bigger than the planets in the solar system. Here's another one. Oops. So this planet was actually one of the first planets found in these transit surveys. It's as big as Jupiter is, and it orbits its star in just 3 days. So it's whipping around right next to the star. We call those planets hot Jupiters. So I've given you 2 examples of systems, neither of which look anything like the solar system. And I think that's kind of a theme for exoplanets, is that whenever we look for planets orbiting other stars, we find lots of planets, the majority of which are very different than the planets in the solar system. So we're perpetually surprised and mystified by what we find, and then we have to go and explain, why does this system look like this versus the solar system looking like it does? Okay, so this is a slightly more kind of detailed picture. So this is now showing all of the confirmed planets that we found. So distance from the stars on the bottom, and this is in units of AU, which is Earth-Sun distance. So Earth is 1. Most planets are closer than Mercury is to the sun. So you can see in yellow, all the planets in the solar system, where they are for comparison. And then on the y-axis is the mass of the planet relative to the mass of the Earth. So, like I said, most planets are close to their stars. And it's also much easier to find big planets than it is to find small planets. So we see a lot of these hot Jupiters, things as big as Jupiter but orbiting much, much closer. We see there's also a population of planets that are like Jupiter. Those actually were not discovered using transits because most of the time they don't pass in front of their star because their orbits are very long. Those were detected using a different technique called radial velocity. So in that case, the planet, as it orbits the star, the planet's tugging the star back and forth. And if we measure the spectrum of the star, we actually see the Doppler shift as the star moves towards us and away from us. So we're measuring the motion of the star caused by the orbiting planet to find those Jupiter analogs. Okay. Then there's this whole cluster of planets on the bottom. So these are things that are not gas giants like Jupiter. They're smaller, still a bit bigger than the Earth, maybe 2 or 3 times bigger than the Earth, but going down to things that are Earth-sized. So we call these planets sub-Neptunes if they have hydrogen envelopes like Neptune, or if they're scaled-up versions of the Earth, we call them super-Earths. All right, so now we have our list of planet types. Now we want to know how common or rare is each kind of planet, because this is just a list of everything we found. This isn't telling us which things are more common or less common. So let's put some numbers down. Okay, so hot Jupiters, there's a lot of them in our plot because they're pretty easy to find. They're big, they're close in, It's a really large signal, it's not hard to see, so we're good at finding them, but it turns out they're pretty rare. So if I pick a random sun-like star in the sky, only about 1 in 100 of those stars will have a hot Jupiter in orbit around it. If we want to ask how many stars have a planet like Jupiter, so Jupiter size but orbiting further out, closer to the orbit of Jupiter in our solar system, that's more like maybe 10–15% of stars like the sun. So Jupiter analogs are more common, but still not the majority of stars. And then lastly, these sub-Neptunes and super-Earths actually turn out to be extremely common. So if I pick a random star, 50-50 chance that it's got one or more of these planets in orbit around it. It's really worth kind of stopping and thinking for a minute about what that means, because I think one of the questions that we asked when we first started looking for planets is we wanted to know whether the solar system was common or rare. So are small rocky planets close in, big gas giant planets further out? Is that like a typical planetary system? Or is that a very unusual, special kind of planetary system? So we can take these numbers and now we can actually say that the solar system is kind of unusual for 2 reasons. One, it's a little bit unusual that we have a Jupiter. That's only about 1 in 10 of sun-like stars have a planet like Jupiter. And it's also unusual because we don't have one of these sub-Neptunes or super-Earths. These very common planets are not a type of planet that we have locally. So we're a little bit different than the norm, it turns out. Okay. So when we do these surveys, we find these planets and we know the size of the planet, but we don't know anything else about it. And so what I wanted to talk about next is how do we then take our list of planets and start to learn more about what the planet is made of. What is the interior made of? What is the atmosphere made of? So pretty universally, if you're a very big planet the size of Jupiter or Saturn, even orbiting other stars, those planets are always primarily hydrogen and helium gas. To grow that big, you grow by getting a bunch of gas. So we know the basic composition of those pretty well. Smaller planets, we don't know as well. So smaller planets, we know their interiors are rock and metal, but small planets can have many different kinds of atmospheres. Even in the solar system, we see that Earth has an atmosphere that's a mixture of nitrogen and oxygen. Venus and Mars, mostly carbon dioxide. And it's possible that exoplanets might also have other things in their atmospheres. So for example, you might have a planet which has a steam atmosphere that's mostly water. Okay, so you might think, if we think about these hot Jupiters, I just told you that their envelopes are mostly hydrogen and helium. So we're done, right? We know what they are. They're big giant planets. We know what they're made of. But it turns out that it's still interesting to look at them in a little bit more detail because they're a little bit of a puzzle. They're really big planets, and if you try and imagine making a really big planet on a really close-in orbit, it just doesn't work. You slam stuff together and it breaks apart instead of growing bigger. There's just a lot of problems with making a planet the size of Jupiter really close to the star. So we think that they probably didn't form where we see them today. We think they probably formed further out, and then something caused them to migrate inwards. But we don't know how far out they were. Maybe they were just a little ways further out. Maybe they were way out at Neptune's orbit. So one of the questions that we want to answer is, can we figure out where hot Jupiters came from? And it turns out we can do that by looking at the mixture of gases that are present in their atmospheres. So when we're building a hot Jupiter, we're accreting a mixture of gas and dust from the protoplanetary disk. And the composition of the materials that we're accreting will be different depending on where we are in the disk. So if we're close in, we have our gas envelope, and then we're raining down little rocks, little bits of rock and metal, and those vaporize and they mix into the atmosphere. If we're further out, that rain of little rocks is actually icy pebbles, so it's more of a mixture of rock and water ice. So the stuff that ends up in the atmosphere will look different if we form further out, where the gas is colder and water is frozen out. versus if we're forming close in, where the gas is hotter, that water stays in vapor, and our little pebbles are just rock and metal. So if we could look and see what the composition of these gases are in the atmosphere, we might be able to tell, did the planet grow by accreting a lot of icy materials, or did it grow by accreting a lot of rocky materials? And that'll tell us roughly where it came from. Okay, but how do we figure out what gases are actually in the envelope of our hot Jupiter? So it turns out that we can use the same technique that we were using before to find the planet, but now we're going to just take it one step further. So we talked about how when the planet goes in front of the star, it blocks part of the star's light. If our planet has an atmosphere, that atmosphere will be transparent at some wavelengths, and it will be opaque at other wavelengths. So the amount of light the planet blocks when it goes in front of the star will change very subtly depending on the wavelength of light that we're measuring it in. So if we look at this planet when it goes in front of the star and we measure the amount of light it blocks as a function of wavelength, we see those wavelength-dependent variations. Those tell us what gases are present in the atmosphere. The way that we make these measurements is using the James Webb Space Telescope. This little wavelength-dependent change is really, really tiny, so tiny that it's quite difficult to measure from Earth. But this is a 7-meter telescope in space. It observes infrared light, where a lot of the main gases that we're interested in looking for absorb. And so it turns out this is actually really good at sniffing out all these different molecules that are present in the atmospheres of these planets. Okay, I'm not going to show you that much data, but I'm going to show you one plot just because it's a really, really cool plot. So this is the wavelength that we're making the measurement at on the bottom. And on the y-axis, this is the size of the planet at each wavelength. So if this was just a ball of rock going in front of the star, we would see the size would be the same no matter what wavelength we observe at. Instead, this is an observation of a close-in hot Jupiter, and its atmosphere is a mixture of hydrogen, helium, and many other gases. And so when you measure its size as a function of wavelength, you see these nice big up and down variations. They're due to a bunch of different molecules in its atmosphere. So in this case, the big peak on the right is carbon dioxide. There's water in blue, more at the shorter wavelengths, but you can see there's this whole kind of forest of different molecules that we can detect and measure in the atmosphere of this planet. So remember, we want to take these measurements, we want to answer the question of, did the planet accrete icy material or dry, rocky material? And so from these measurements, we can go back to our cartoon story here, and we can see that in this case, the planet probably had more icy materials, and so we think that this particular planet came from somewhere near the water ice line where those materials were frozen out. And it turns out that is most, for pretty much all the hot Jupiters that we've looked at, that seems to be the answer. So that's telling us that maybe these systems started out with something like Jupiter further out, but unlike in the solar system, that planet was then migrated inward. Okay, so hot Jupiters formed further out and then migrated in. So their atmospheres are going to be made of very similar mixtures of materials to the Jupiter analogs, which formed further out and then stayed further out. But what about the smaller planets? Those get a lot more complicated because when you're small, you don't have to be mostly made of gas. You can have atmospheres that are made from many different mixtures of material. And we don't even have any solar system analogs here to compare to. So we can't even make any predictions like it's big like Jupiter, maybe it has the same mixture of gases that Jupiter does. We have no idea what to expect for these small planets. Okay. So we want to study the atmospheres of small planets, but we have a challenge. And that challenge is this is now to scale the hot Jupiters we were looking at before, and then next to it, I'm showing you the Earth and Venus. So we're going from studying something that's really big, and that means the signals we're measuring are pretty large. You saw those were pretty easy to see in that plot. Now we're going for something which is much, much smaller, And the predicted signal that we're looking for here is now something like 1,000 times smaller. We're talking about detecting an Earth-like atmosphere versus a hot Jupiter atmosphere. It's a big difference. It's a much harder signal to see. So if that was it, same measurement, 1,000 times smaller, that's not something we can do with the telescopes we have today. We would need to build a much bigger telescope and launch it into space before we could see that kind of signal. But that's going to be really expensive, and it's going to take a really long time. I'm not very patient. I would like to do this now, rather than waiting 10 years or 20 years and hoping that NASA decides to build a bigger telescope. So it turns out there's a shortcut. And that shortcut is to stop and think about what kinds of systems we're looking at. So we've been thinking about stars like the sun, but stars come in all different sizes. Many of the stars that are closest to the Earth are actually much smaller and much cooler than the sun. So we call those little stars M dwarfs, and they can be something like half the size of the sun down to maybe about 10% the size of the sun. So imagine I take my Earth-sized planet, and instead of having it pass in front of the sun, I instead have it pass in front of one of these little tiny M dwarfs. That same planet is now going to block much more of the star's light because I've shrunk the star. So by looking at those kinds of systems, I can boost the signal size and get it back big enough to something that I can feasibly detect with the telescopes I have today. So I'm going to tell you about what we're learning about the properties of small planets, but every one of those small planets orbit stars that are much smaller than the sun. So none of those planets are really Earth-Sun analogs. Okay, we got to think about that for a minute because these stars are much smaller and dimmer than the sun, and it's possible that they just form different kinds of planets. So when you have a smaller and dimmer star, the gas disk surrounding the star is going to be smaller and it's going to be colder. The disk is colder, then you're going to freeze out your water vapor into ice. So one theory is that the planets orbiting these small, dim stars might tend to very frequently accrete lots of water ice. So you might see a lot of planets with water-rich envelopes orbiting these small stars. Picture something like the icy moons of Jupiter, like Europa or Enceladus, but scaled up to planet size. That's the sort of thing that we might possibly find. Okay, there's another big difference, which is these little stars are dim, but they're also very magnetically active. So, you know, those big solar storms that we had a couple months ago that made the nice aurora, imagine that, but scaled up and all the time. So these guys are flaring all the time, they're emitting all sorts of high energy radiation, and all of that is actually going to erode the atmospheres of these planets much more quickly than they would if they were orbiting the sun. So one other possibility is that planets orbiting these kinds of stars often don't have atmospheres because the star has just stripped away all that gas. Okay, so now let's go and look at some of these planets. So first, let's think about these water worlds. So planets that rocky core, but then throw on a thick water envelope on top. If the planet's close in, that might be steam. If it's further out, it's possible that you could have a liquid water ocean. So this planet, TOI 270d, was found just a couple years ago. And you can see it's pretty typical of these intermediate planets. So it's about half the size of Neptune, but about twice the size of the Earth. So it's really kind of intermediate in size. When we measure the mass, it's about 5 times the mass of the Earth. And so mass and radius gives you density. We know that it's not just a ball of rock. It's not a scaled up Earth. We know that it has to have some sort of puffy envelope on top. But we don't know whether that puffy envelope is made of hydrogen and helium gas, or it's a puffy envelope with a lot of water in it. The planet is relatively cool. It has a predicted temperature of only about 200 degrees Fahrenheit. By Earth standards, that's kind of uncomfortably hot, but for exoplanets, that's definitely on the cool end. And it's even cooler than the surface of Venus. So it might be a little bit too warm for liquid water, but you could still have a steam envelope, or possibly, if it's a little bit reflective, it could maybe get cool enough for liquid water. Okay, so we don't know whether it has a hydrogen-rich envelope and a little bit of a bigger rocky core in the middle, or whether it has a slightly smaller rocky core with a water vapor envelope on top. So we can figure out which of those it is by looking for absorption from its atmosphere when it passes in front of its star. So this is now the same technique that we were doing before, but for a smaller and colder planet than before. So smaller signal, but we planned for that, and we've cleverly picked a planet that orbits a smaller and cooler star, so we're still okay. This is something that we can do with the James Webb Space Telescope. Okay, so this is what we see. So this is the same measurement. So this is wavelength on the bottom and planet size on the y-axis. So you see the planet size changes depending on the wavelength we're measuring at. And those up and down wiggles are due to the presence of different molecules in its atmosphere. So I know that legend is kind of tiny. So the three most important molecules that we see absorption from methane, we see absorption from carbon dioxide, and we see absorption from water. However, if we think about how much water there is relative to those other gases, we find that it is not a water world. So it's not a steam atmosphere. It's actually an atmosphere with a mix of multiple different molecules. And it turns out that by mass, it's actually about half hydrogen, helium, and half these other molecules. So this turns out to be more like a scaled down version of Neptune and less like a water world. Okay, so haven't given up yet. The first planet we looked at was not a water world, but maybe water worlds are out there waiting to be found. So there's actually a survey right now where the James Webb Space Telescope is looking at something like 5 to 10 of these planets, which are small enough and cool enough that they might be water worlds, but we don't know yet. And so if we look at all of those planets and we don't see water-rich envelopes around any of them, then we'll know that these water worlds either don't exist or are relatively rare, but we may find a couple. And so stay tuned. Okay. So the last part of my talk, I promised that we would go from big planets all the way down to planets like the Earth. So now we've talked about intermediate-sized planets. Let's try and take it all the way down to Earth. So one of the big questions that we'd like to answer with all these surveys and all these studies is, how common or rare are planets like the Earth? So I pick a random star, I have my Star Trek spaceship, I go to visit it. What are the odds that it has a planet that I might want to actually visit, that might have liquid water on the surface that could potentially support life? So we know how common Earth-sized planets are. So we want the planet to be Earth-sized, and we want it to get about the same amount of light from its star that the Earth gets from the sun. We don't want it to be really hot or really cold. We want it to be kind of a nice temperate in between. So we know that planets that are about the right temperature and about the right size are, let's see, about 1 in 3. So I pick a random sun-like star in the sky, 1 in 3 chance that it'll have a planet the size of the Earth and about the same temperature as the Earth. But that's still not enough to tell me if it's a place that I would want to visit in Star Trek. So let's think about the 3 rocky planets in the solar system. So if we look at Venus, Venus has a very thick carbon dioxide atmosphere that blankets it and heats the surface. The surface of Venus is way too hot to ever have liquid water. Definitely not a place you'd want to visit. Not habitable. Mars is much further from the sun. Heat, not a problem, but Mars has a very thin atmosphere, also carbon dioxide, but much, much less. So Mars doesn't get enough sunlight, and water on the surface of Mars is frozen. It's very cold. So also not a place I'd want to visit, at least not without a spacesuit. But the Earth gets a little bit more light than Mars and a little bit less than Venus. Oh, yes. So we shouldn't write off Mars entirely, because if we go back in time, Mars had a much thicker atmosphere, and so early on, Mars actually did have liquid water on the surface. So it's not that Mars is doomed because it's too far away from the sun. Mars is doomed because it lost too much of its atmosphere and then it got really cold. Okay, on Earth, we're doing pretty well. We're a good distance from the sun. We have just enough atmosphere to keep us warm, but not too much atmosphere to overheat things. So all this to say that if I just gave you a list of here's 3 planets, here's their distance from the star, tell me which ones are maybe habitable, I wouldn't be able to give you the right answers for the planets in the solar system without knowing what kind of atmospheres they have. So if Earth had a much thicker atmosphere like Venus, we would be in big trouble. And if it had a much thinner atmosphere like Mars, also would not be a place we would want to live. So atmosphere is really important for habitability. All right, so if we want to answer this question for exoplanets, we want to find rocky planets. We want to know whether or not they have atmospheres. We need to know what kind of atmosphere they have. What's it made of? How thick or thin is it? So we need to actually go and detect some atmospheres around rocky planets. So people have been trying to do this ever since the James Webb Space Telescope was launched a couple of years ago. When I looked recently, I was able to make a list of 4 planets that they've observed so far. So TOI 836, I'm just going to give you their telephone numbers. LHS 475, these are just named after the surveys that found them, and the number tells you the order that it was found in. GJ 341, that's a number from a star catalog, and GJ 367 is another star catalog. So astronomers are not good at naming planets, I apologize. All right, so these planets are, one of them is a little bit smaller than the Earth, a couple of them are slightly bigger than the Earth, but these are all planets that we're pretty sure are rocky and Earth-like. Looked with the James Webb Space Telescope when the planet went in front of the star, measured the size as a function of wavelength, nothing. No detections, no signs of any atmosphere. Does that mean that they don't have atmospheres? It turns out that we might have missed it. So the problem with looking for atmospheres like the Earth's atmosphere is that they're very, very thin. So this is actually an image taken from the International Space Station. So that blue arc is actually Earth's atmosphere. And so you can see like Earth's atmosphere is tiny, it's very thin compared to the size of the Earth. So in my little cartoon, where I drew that blue circle that represents the planet's atmosphere, if I'm drawing that cartoon for an Earth-sized planet, you wouldn't be able to see the blue circle. That's how thin it would be. So it's possible that some of those planets have atmospheres, but we wouldn't be able to see them because they're so thin, and that therefore the size of their signal when they go in front of the star is very, very tiny. So is there an easier way to look for atmospheres? It turns out there might be. So if we look in the solar system, Mercury is the closest planet to the sun. Mercury has basically no atmosphere. And if we were to measure the temperature on the surface of Mercury, you would see that the day side of Mercury is very, very hot. So when it's illuminated by sunlight, the day side gets to be 800 degrees Fahrenheit. That's hotter than most ovens will go. But the night side, which is hidden from the sunlight, the night side gets down to minus 290 degrees Fahrenheit. So because Mercury doesn't have an atmosphere, the day side is really hot and the night side is really cold. If we were to throw an atmosphere on top of Mercury, that atmosphere would take heat and carry it from the day side to the night side, and it would kind of even everything out. So on Earth, it gets a little colder at night and a little warmer during the day, but those temperature changes are very small, and that's because we have an atmosphere. So if we could measure the day and night temperatures on these planets, we could tell whether or not they had a thick atmosphere, or at least thick enough. So I'm going to show you a measurement for one of these rocky planets called LHS 3844. This planet is a little bit bigger than the Earth. It's about 3 times the mass of the Earth, rocky planet. And if we ask what temperature it is, it gets a little bit more light from its star than Mercury does from the sun. So it's going to be pretty warm, but it's also much bigger than Mercury. So maybe it has an atmosphere, maybe it doesn't. Okay, how do we measure the temperature of a planet? So if we wait, we see the transit when the planet goes in front of the star, We wait about half an orbit. The planet's going to go around behind the star and it's going to disappear and reappear. So if we're measuring the brightness of the system at infrared wavelengths, where the planet emits and the star emits, we're going to see a small dip when the planet disappears and then reappears. And that dip is going to tell us how much infrared light is emitted by the planet. If we actually continue our measurement and watch through a whole orbit, we're going to see the infrared light from the planet get brighter when the day side comes into view and gets dimmer when the night side comes around into view. So we can use that to measure the day and the night side temperature. Okay, that went by kind of fast, so let me show you what that actually looks like. So this is our rocky super-Earth, LHS 3844. We're going to start when the planet goes in front of the star. So on the left, we're seeing the night side of the planet. And we're watching as the day side comes around into view, and we're measuring the brightness of the planet at infrared wavelengths. So hotter day side is going to be brighter in the infrared. Dimmer night side is going to be colder in the infrared. So brightness maps to temperature. Day side comes around, it's much brighter. Now there's a dip in the middle. That's when the planet disappears behind the star and reappears. And then we see it get dimmer again as the night side comes back around. So we can take this and we can map a temperature. So it turns out the day side of this planet is about 1300 degrees Fahrenheit, even hotter than Mercury. And the night side is so cold that we don't detect any light from it at all. So we know the night side is much, much colder and the day side is quite hot. That must mean that it has very little or no atmosphere. Because in order to get the day side that hot and the night side that cold, you can't have anything carrying heat around from the day side to the night side. Okay, so maybe that shouldn't surprise us. This planet is hotter than Mercury is. When planets are really close to the star and their atmospheres are hot, it's easy for them to lose those atmospheres. So maybe we need to look at planets that are a little bit further away from their star. That's something that we're doing right now. So the James Webb Space Telescope is doing a survey of rocky planets at a variety of distances. And so what we're hoping we'll see is as we get further away, eventually we start to see planets that have kept their atmospheres. But in the meantime, we have an opportunity to do something different. We know that this planet doesn't have an atmosphere. It's a bare rock like Mercury. So that means when we measure light emitted by the planet, we're measuring light emitted from the rocky surface of the planet. That rocky surface could be made from many different types of materials. And if we measure the spectrum of the light from the planet, we might actually be able to tell what its surface is made of. So just to kind of orient ourselves in the solar system, so we think about 3 of the rocky planets. We're going to ignore Venus, because Venus's atmosphere hides its surface. We actually don't know much about the rocks on the surface of Venus. But Mars, Earth, and Mercury, that they're sort of broad classes of rocks that describe big regions on the surface of each of those planets. When I plot the images of those rocks, just like that you would see with your eye, you can see that the rocks are different colors. But if I was to observe those rocks with a spectrograph, I would see that each of those rocks would have a distinct spectrum. So you could think of it like a fingerprint that tells me exactly what kind of rock I'm looking at. So if I take models for that same set of rocks and I predict what the brightness of the planet will be as a function of wavelength, and now I'm plotting brightness of the planet relative to the brightness of the star, because that's what I'm measuring when I measure that secondary eclipse, you can see that those colored lines have different shapes. Some of them have a dip in the middle of the wavelength range, other ones look pretty flat. So if I can measure that spectral shape, I can tell you what kind of rock is present on the surface of that planet. So this is actually the first time I've had real conversations with my geology colleagues where I get to say, you guys study rocks. I have rocky planets where I think I can actually get a spectrum. If I show you a spectrum, can you tell me what kind of rocks are on the planet? And so we're working on that right now. I think the data are almost good enough, but not quite good enough yet. But it's definitely something that we can do in the near future. Okay, so we have covered a lot of ground. And so I thought it would be good to take a step back here at the end and just remind ourselves in our grand tour, what are some of the different kinds of planets that we talked about? So we talked about these big gas giant planets like Jupiter that are right close to their star. They're very hot, they're big, they're puffy. And we think that those planets didn't form where we see them today. We think they started further out, near where Jupiter is, and then something caused them to migrate in. So when we say, why do other planetary systems look different than ours? One answer might be, do we know whether their giant planets more or less stayed put or moved around? We also asked whether some of these smaller, cooler stars might form planets with thick, water-rich envelopes. Maybe some of those planets could even have liquid water oceans. We're looking for water worlds. We haven't found any yet, but we think they might exist. And if they do, we'll probably see them within the next year or two, unless they're very, very rare. Lastly, we have the ability to detect the atmospheres and maybe the surface compositions of rocky planets that are maybe hotter than the Earth, but still terrestrial, things that are similar to Earth, Mars, Venus, and Mercury. And we haven't detected those signals yet, for the most part, but it's definitely something that we can do now with the James Webb Space Telescope. So give it another year or two to kind of build up more data, and I think we're gonna get there. All right, so that is the whirlwind tour of all the different kinds of planets. Again, if there's a theme here, that theme is exoplanets are weird. We keep finding planets that we didn't expect that look different than the planets in the solar system. And that gives us a neat little detective story to solve in order to understand why do these planets look so different? What happened? We started out at the same point. What are the forks in the road that cause us to end up with one kind of planet versus another? And so that's been a fun detective story to work on. All right, with that, I'm going to end and take questions. Yes?
How often, if at all, do you discover any abnormalities when it comes to exoplanets in terms of their shape, like how they're all traditionally round, or whether their orbital paths are similar to what we know as the usual circular orbital path? Have you ever encountered any abnormalities in those two things, like the shapes and the orbital paths?
Yeah, so the question is, I've talked mostly about what the planets are made of and what their distances are from the star, but there are other things we can look at. One is, are the planets all spherical? They're actually not perfectly spherical because they're rotating, and that's going to squash it a little bit, so they're going to be slightly flattened, but we have not yet detected the flattening from rotation for any of the exoplanets. If they had rings like Saturn, that would also change the shape we see when the planet goes in front of the star. Haven't seen that yet, must be out there somewhere, still looking. They also, their orbits have a wide range of eccentricity. So eccentricity is just, do you always orbit the star at exactly the same distance, or do you sometimes come closer and sometimes further? Lots of planets have eccentric orbits where they're going closer to the star and then they're going further away. That's another thing that's a little different than what we see in the solar system, where things are pretty close to circular. Yeah. Yes?
What's making these hot Jupiters get closer to the stars?
Yeah, that's a great question. So I said that they must form further out and then migrate in, the hot Jupiters. Why do they do that? There are two main ideas that people have. One is that when the planet's embedded in the gas disk, that gas is like a headwind on the planet that drags on it, it slows its velocity, and that causes it to spiral inwards along with the gas. The other idea is that you have two planets that come close and they maybe scatter off one another. So one planet gets scattered in, one gets scattered out. There are other ways to alter the orbit by sort of three-body interactions. Another star could do it as well. Still don't have a clear answer, but I think most evidence at the moment is leaning towards three bodies. So it's either an encounter with another planet or another star that sent it inwards, probably for the majority of hot Jupiters, but there's not like a open shut 100%, it's got to be that and nothing else kind of evidence yet.
Yeah, it's amazing those orbits are stable.
Yeah, you commented it's amazing they're stable. Mostly they are. There are one or two examples where we see the hot Jupiter is so close that it is spiraling inwards and is going to fall onto the star at some point, not any time in our lifetime. But yeah, most of them are okay where they are. Yes.
One of the things that makes life so possible on this planet is our moon. So the question is, exomoons. You know, there must be some sort of an effort, I would think, to look for something like that.
Yeah, so the question is, have we found any evidence for moons around any of these planets? It seems so obvious that they should be there. If we look at the giant planets in our solar system, all of them have multiple moons. The Earth has a moon. One explanation might be that we're mostly looking at planets close in, and maybe the process of migrating strips away moons, especially if it's some sort of scattering event. So people have tried to prioritize looking at more distant planets in hopes they're more likely to have moons, but I think the other part of the answer is that we're not sensitive to moons as small as like the moons of Jupiter. If we had an Earth orbiting Jupiter, we could see that, but we probably are missing a lot of the moons that are more analogs to what we have in the solar system.
Are there any programs that are specifically going to start looking for this sort of anomaly?
There are definitely people that are actively looking for moons. Yeah, but haven't found any yet. Yeah, questions on this side? Yeah. Yeah, go ahead.
I have two questions. The first one is, you mentioned that the solar system is unique in two ways. One is that we don't have, or we have a Jupiter, and the other is that we don't have a sub-Neptune or a super Earth. First question is, have you noticed any like correlation or anti-correlation that if a planet has a Jupiter or a super Jupiter, it doesn't necessarily have a sub-Neptune, or vice versa?
Yeah. So your question is, we're unusual because we have a Jupiter, and we're unusual because we don't have super Earths or sub-Neptunes. Could those two things be connected? It's a great question. We went and looked a few years ago, and it seems like the answer is no, that you're actually more likely to have a Jupiter if you also have a super Earth. So it's not like having a Jupiter somehow prevents those big inner planets from forming. It must be something else, but it's a great question.
The second question real quick is probably pretty naive, but have you looked into possibly doing some kind, you mentioned that it's hard to study atmospheres and chemical composition planets, Earth-like planets orbiting around G-class stars. Have you looked into like kind of doing a stacking analysis? Is that something that's possible where you look at the sample as a whole to identify something, or is that?
Yeah, so you're asking, can we find atmospheres around really small planets by taking data for a bunch of them and stacking them together? That would work if they all had the same kinds of atmospheres, but if they had different ones, the stacking might smear it out. Yeah, it's a good thought. People have done things like that, but yeah, it's a tough problem even with that. All right, question right here.
How many moons does Jupiter have?
Jupiter has a lot of moons. There are 4 big moons, but it has even more little ones.
I think it has like 67 moons.
I believe that. I can't even tell you the number. That's how many it has. Yeah, all of our giants have a lot of moons.
Yeah, my computer said that it had about 67 moons.
Yeah, every time we look at our gas giants, we keep finding new moons that we didn't know existed before. Yeah, that's why if I had to bet, I would bet that some of these exoplanets must have moons, because moons are so common in the solar system that it would be kind of crazy to think that they don't also form around these planets. Yes?
So you mentioned that we're looking for habitable, potentially planets similar by the size, like the Earth, right? Why not bigger or smaller?
Yeah, so the question is, could you have habitable planets that are much bigger or smaller than the Earth? Yeah, it would be nice if there were bigger planets that are habitable, because bigger planets are easier to find and easier to study. So one of the reasons people got really excited about the idea of water worlds is that water worlds are much easier to detect and characterize. So if any of them have thick water envelopes that are cold enough to make oceans, we think maybe a world that's just a global thick ocean could also be habitable, potentially, even if it's not exactly like Earth. Planets smaller than the Earth, the main problem is that it's harder for them to hold on to their atmospheres, and once you lose your atmosphere, then you're sunk. Your atmosphere, your surface is going to be really hot in some parts and really cold in others, and no liquid water anywhere. But smaller planets can definitely be habitable. Mars was probably habitable and had liquid water in the past. So that's the main game, is you gotta be far enough away from your star to keep your atmosphere so you can stay habitable. Yeah. All right, yes.
With having a hot Jupiter system, assuming that it's losing its atmosphere due to temperature, would it automatically disqualify the system from having any sort of habitable planet? Or, well, for two reasons, I suppose. Because number one, with the hot Jupiter moving in close to the system, completely disrupt the orbit of other planets in the system. And two, with the gases going off of it, screwing the atmospheres of planets from there on out?
Yeah, so what does having a hot Jupiter do to other planets in the system? So you're right. If the hot Jupiter gets to where it is by just plowing through the inner part of the planetary system, it's going to eject any smaller planets that were previously there. So when we look at systems with hot Jupiters, we see that the hot Jupiters are lonely, that there are no nearby planets. So there may be more distant planets, but yeah, in general, they're probably not great places to look for Earth analogs. The escaping gas from the hot Jupiter dissipates pretty quickly. So even if you were a nearby planet, you're not going to be affected by that much at all. But we can actually see gas being blown off the tops of hot Jupiters, so they are losing a little bit of their mass. All right, maybe one more question. Yes?
It's kind of a different kind of question, but you grew up in a really interesting place, very remote and small. And I would think that shapes kind of your perspective of the world or your place in it. And I was curious if the place where you grew up, if it impacted your interest in astrophysics specifically.
Yeah, so I grew up on a little island in the middle of the Pacific Ocean. It was actually a military base, so it was kind of like small town America, but it was a beautiful place for stargazing. It was really dark at night. I definitely went out with little telescopes and looked at the night sky. I was always fascinated by space and the stars, but I don't think I ever thought of it as like a career that I could do until I went to college. And even in college, I only ended up doing it because I was at Johns Hopkins, and Johns Hopkins is the home of the Hubble Space Telescope. And that was right across from the building where I had all my physics classes. So it was like right there in front of me, and it was just so tempting to go, during the summer and do research over there. So I kind of got pulled into it, but it was not a plan that I had since I was a kid. All right, I'm gonna wrap it up there. I know there's telescopes outside. So thank you guys for coming. I hope you see some good stuff tonight. It's clear.